Så da vil jeg ønske velkommen til et ekstraordinært frokostmøte i Arkitektenes hus. Det er et møte, mitt navn forresten er Stein Stoknes, prosjektleder i FutureBuilt, og skal være møteleder i dag. Dette møtet er et samarbeid, et ekstra frokostmøte, samarbeid med Norske Arkitekters Landsforbund og FutureBuilt, og det er støttet av både Statsbygg og Fremtidens byer. Vi var arrangert en studietur sammen FutureBuilt og NAL til Zürich og Sveits, og da var innom ETH og traff professor Leibundgut. Han holdt et foredrag som skapte både debatt og litt, hva skal jeg si, provoserte, men også inspirerte. En ting var at han avfeier lavenergi og passivhus som strategi, og ber oss fokusere på energiproduksjon, sol, jordvarme i stedet for. Og dette er jo vranglære. En annen ting er at han også i forma var litt sånn provoserende. Han er både nysgjerrig og nytenkende og charmerende, men også ganske sånn belærende. Kan han være. Så det er mye å ta fatt i. Han er både spissformulert, men også vitenskapelig korrekt. En spennende mann. Og så var det sånn at Statsbygg syntes det her var så interessant at de inviterte han opp hit nå for å ha en workshop. Det hadde de i går, og de var så rause at de tilbød oss å kjøre et åpent møte i dag. Så her er vi. Og møtet kom i stand veldig fort. Vi annonserte på mandag, allerede på tirsdag morgen var det fulltegnet, med 10 personer over. Så det var over all forventning. Og i løpet av uka det strømmet på. Det er over 200 påmeldte, og alle får dessverre ikke plass. Så derfor har vi rigget til streaming, for dem som ikke fikk plass å sitte hjemme. Men det blir nok bra det også. Men i hvert fall fantastisk med sånn respons. Og så over to English, Mr. Leibundgut. We are very happy, National Association of Architects and FutureBuilt, to be able to invite you here, to hear your speech again, for us that we're down there in the city to meet you there. Happy to be able to introduce your Sol2Ergie, is that correct? Concept to a broad audience with here 160 representatives from the building industry. We also have some representatives here from, or maybe all, a board responsible for suggesting new building regulations. And I'm sure they're eager to listen to what you have to tell them. I'm sure you have some provocative opinions, and I'm sure they have some good questions for you as well. So, I'll ask you to come up here. Welcome to Hans-Jørg Leibundgut.
So thank you very much having invited me. I'm overwhelmed. It's not the amount of people or the number of people that impresses me, that the way you sit. And the distribution. Normally in Switzerland there are about 1% women and 90% old men. And if I look around, it's a different audience. So let me introduce myself, because it's important. You know, yesterday I had a lecture and that was very theoretical. And people would think that I'm a theoretical guy. But actually I'm a practical engineer, and I came out after my study, I studied nuclear engineering in Switzerland because I was very keen on the possibilities of modeling a nuclear reactor with physics and with mathematics. But I failed with the computer work, so I switched to solar energy in 1975. And I worked together with my friend and with Taliban scholars in Afghanistan, and we built up a cheese factory that worked. And the Taliban people, they didn't know anything about plumbing and whatever, so we did it. And it was a first cheese factory with about 120 square meters of solar collectors, producing 3,000 liters of milk and transforming into about 250 kilograms of cheese a day. So afterwards, when the Russians went in Afghanistan, we had to switch because we could not continue. So we went to Portugal and we started again there. So first we had to have a welding experience course, and so I was educated as an approved welder, because we worked with ammonia at a pressure of about 25 bar. So you have to be accepted as a welder. So just I want to say that I'm not talking about things I do not understand in practice. So yesterday I spoke about a building we finished 1.5 years ago. That is my own building. So I invested all my money I have, no more than my money is a part of the money of the bank as well. And I did the most problematic and risky experiment I ever did in my life, to combine all the user systems I did not understand correctly when I started to plan it. So under the way, I had to fix it, and half an hour ago, my wife phoned me and said, "Well, I have a problem. There is some sound in the system because we changed on Monday morning an important part. I will show you an important part of our equipment." So we are still in investigation of the system. But coming back to theoretical background, I think I would like to show you the question of philosophy. It is a question not of technology only. It's a philosophical question, how we deal with energy. And I decided to redo the presentations from yesterday, and I did it new. So I made a combination of a presentation I held in Engelberg in September, and this one of yesterday with the thing. So the question is, why do we build buildings? That has to do with mankind, with human being. We do not have a fur, and we do not make winter sleep, so that we have survived in this climate as here, and we want to have an interior condition that is different from outside. And that is the problem in a country like this, or in Switzerland. We want to have it warmer than here. And we know that if we have warmer, and here's a potential difference, there's a part of the physics, and then we have to replace this flow, and we create a flow because there's a temperature difference from here to here. And everything what is done is with regulation is increasing resistance against this flow. That is the thing. But why? Why is this like this? Why did it occur? So people realized in the past 200 or 5,000 years, that they did not have any insulation material on the walls. That did not exist 100 years ago. So they know they had to provide energy inside and burn it inside to provoke a flow that withholds this temperature difference. And that is actually the energy that is used. That was energy, the only energy, and it grew up on the surface of the earth and has produced by solar energy in a time of about 40 years. These trees that have been cut had an age about 40 years or 50 years. It is not worthwhile to cut a tree with 1 year. This is too slim. So you wait 40 years, then you cut it, and you shift it up like this. You have to wait 1 year until it's dry, otherwise you have too much smoke and so on. And then you burn it in order to prevent, to organize this flow that is accepted. And that was 500 years like this. So, and after in about 1820, that was one guy, the Newcomb, and afterwards James Watt, they invented a steam engine. And the steam engine is this one here. that has nothing to do with burning coal or oil. That is a machine using the second law of thermodynamics that has been invented first by Clausius, and then with the help of Carnot, one of the most important papers in the world up to me. That was the baseline for making this machine that produces mechanical power out of energy, of heat. And it is in 1878, this machine, is a printing machine behind it. This machine runs a printing machine in the center of a parabolic mirror. And unfortunately, this development of this machine with solar energy did not continue. In the same time, Mr. Otto and Mr. Diesel invented the diesel internal combustion engine, and unfortunately, or fortunately, we don't know, there was the distinction or the development of petrol and of refining this crude oil things what you could not use. So they invented things that came together to have an explosion motor running. But this would not have worked only. It was Daimler who invented the ignition and the automatic ignition. So they could start an engine and they could stop it again. But that is not a car. So you have to get a gear, you have a clutch, you have wheels, and so on and so on. And I want to say, the explosion of motorization is only due to a system, and this system belongs together. Otherwise, there's no car. There's no motorcycling like we have. And the same thing is in all energy systems. If you look at a burner, an oil burner or a gas burner, the hell of amount of material that belongs together to run a system with an oil burner. You have to have a drilling machine to drill oil in the shelves in front of Norway. You have to have pipings, you have to have refineries, you have to have a burner, you have to have a tank, a chimney, and so on and so on and so on. And it lasted about 20, 30 years until this system has come to this competence and this cleverness and this reliability like an oil burner and a gas burner. And what we do now is we reinvent a new system not using chemical materials. And that's the thing we have to avoid combustion. Now, if I go to architecture, in the 17th, 18th century, there's houses building like this, and you see that there's not much windows because the material of the window, the glass, was very expensive, and so they had zinc glazing, and they had one choice, not had two choices. Either you have a really bad odor inside, or you open the window, and if you open the window, it's cold. So the problem is stinking or freezing. You have to decide. And that was this kind of housing until about the end of the 19th century. It was a bad housing, and we have not toilets, water toilets, and so on. And then came this revolution, the revolution of the Bauhaus. Was the result of the Industrial Revolution, producing cement, glass, as a float glass, steel for these profiles, and this material where you can cover flat roofs. We call it Dachpappe. I don't know the English expression. That are the four elements that are needed to construct this building that you know from Corbusier and so on. That is that building, new building. It's not this building, but that is a new kind of building. And it is for me, most elegant construction what you ever had, reduction to the minimum what you have. You have a plate where you want to walk, you have a plate that shelters you, and you have pillars and some envelopes that protects you from wind and rain and so on. But they do not work. That's a problem. These buildings, it is not easy to refurbish. We have some buildings like this in Switzerland and in Germany, and all the people who bought these buildings, they came to me and said, can we refurbish? Because we don't want to destroy these Mies van der Rohe buildings and so on. And the problematic side inside is they have not heating systems for the floor heating system, but have radiators. They use temperatures for heating at 50, 52 degrees centigrade. And that's the biggest effort we have to do. So I have refurbished one of these buildings, and it is in operation now since in November 2011, and it works good. But the owner had to invest a lot of money, but they said, well, if I pay 3 million Swiss francs for my nice building from Ernst Giesel in Switzerland, I have to afford the refurbishment of this system. I come later on with this thing. So what happened afterwards? The thing is that does not work and on the long run. And in 1973, there was a shock in oil price. It's just when I finished my diploma, this was the shock of oil price. We didn't have anything in my teaching and my education of energy. Energy was just a term of work, mechanical work, but energy was not in the awareness of people until 73, and then it changed dramatically. And there two things came out. The one is in the southern part of Europe, we started to invent systems, active systems, to transform solar energy into heat or whatever, the heat pump and so on. And about 2 years later, the industry started to produce this isolation material. That is not very long. From the tradition, you have to melt glass or melt rock and to expand it and to do things like this. So it was a battle, it was a fight, active systems against passive systems. And in the last about 20 years, the passive system industry, they won the battle. They thought they won the battle. So what is the result? We have systems like, we have passive house systems because it is possible to build a resistance against thermal flow. And it is not very, very common and not very elegant to have active systems because they fail and they are not elegant and they have all these problems. So, but I'm a mechanical engineer, so and I'm not a guy who produces this isolated material. I'm a mechanical engineer, understanding the second law of thermodynamics and so on. So if you go back to the question of energy, that is the energy production side of the world. Actually, it's the wood, it's the forest. And what is the forest? The forest is the transformation machine from solar energy into biomass. And this efficiency of this transformation is so bad, it's about 0.5% of the solar radiation is transferred into biomass in the wood. And although this efficiency is so bad, we have this beauty of nature, of this variety of tropical forest and of tundra and so on. Just that means we have a real abundance. We have an overwhelming abundance of solar radiation if nature can produce with so little efficiency, such a variety of organisms. The second interesting thing of the forest is that is an inherent storing system. The energy is stored in the wood, is growing, and then we have the possibility to cut the trees, or if we use coal and oil and so on, there are trees that have been grown up for 100 years, fallen down, are covered with mud and carbonized, and they waited this, because the trees waited for 200 million years until they have digged out by people or drilled out by people, Norwegian people like this, and producing a mess in the atmosphere. So now I think we are really in a real mess. I think we overcome the point of no return in the development of temperature and situation in the atmosphere and the ocean. Unfortunately, we missed the point, but there's still a possibility that we lower down the velocity of these changing systems. So doing this, adapting this to this development what we have to accept. We have to rely on the real source. The primary energy source is the sun. It's not oil. That is a secondary source. It's oil and coal and gas. It's just stored solar energy that has been produced 200 million years ago. So the question is, how can we deal with the actual sun, with the young sun, the old suns? How can we deal with the young suns? So, and that is the first invention. We know since about 1952 only that we can produce with a physical phenomena called photovoltaic system. We can produce electricity out of solar radiation. That is the biggest invention I think mankind made since hundreds of years. It is not realized what it is actually. You take a tiny little sheet of material of about 3 micrometers and expose it. This is silicium, and dot it with boron or phosphorum and add it a little bit of copper and the backside, and you produce 20%, that's the average now, 20% of energy in form of electricity out of solar radiation. So this material, this sheet, is about 40 times better than the natural system of photosynthesis. It transfers the solar radiation 40 times better than a tree. So knowing that if you have a black plate and you take out 20%, this plate becomes warm, becomes hot. And we call it the Leerlauftemperatur at zero output temperature. When you do not extract heat, that is the temperature, maximum temperature the plate can get. There's about 80 degrees if it is not isolated, 80 degrees warm. And we know that the electrical efficiency decreases with heating up or with the temperature of this plate. So what we did, we just we cooled that collector. That is a grid now, and that is the second version of thing what we did. That is a plate, a normal aluminium plate with a thickness of 0.5 millimeter with a bended tube unwelded and is sucked with vacuum to this backside of this plate. And what happens now, that is results of my house. So my house was the first house, I think worldwide, where I have installed 28 square meters of this hybrid collector, producing electricity and producing warm water in the same machine, the same apparatus. Though that is the normal, that is the electrical output, and you see we had to, because that is the thermal output. And the thermal output is about four times bigger than the electrical output. So we increase the efficiency of the system by a factor of 4. So then we are in a number of 150 times better than the wood. And that is the point. That is just using technology and exposing to solar radiation, that the actual radiation. Now we see that obviously we have this peak in summer. And this is true for a temperature of 25 to 30 degrees centigrade out of this solar collector. So, and you can again ask yourself why it took so long that these things has been invented or manufactured. Because nobody knew what to do with this amount of energy at 25 degrees centigrade in summer. It's just useless. You do not have to heat, so you cannot use for heating. You cannot use it for showering because it's too cold. So the thing is, what the hell should we do? So the thing is, you can integrate this, and these you see here. Unfortunately, I could not move the crane. That is the solar collector up on my window. I took the photo 3 days ago. So that is what the house I spoke yesterday, the picture from last, I think, Monday. So now the question is, if we have a system that produces solar energy if in abundance in summer, what are we doing? So the problematic thing, it is also a problematic thing of all these regulations. They always look at the building envelope. If you open up your mind and go into environment, the first thing, where do you go? Up, down, where? So we went down in the thing. So if you go down in the earth, underneath your terrain, and it belongs to you, that is the part of your terrain. And what I say, if you have an infrastructure of a construction site, you pay for it to bring it into the connection of traffic. You have wastewater disposal, you have freshwater access, and so on. And what I say, a construction site consists of a hole in a depth of 400 meters in order to bring down the energy in summer you have produced with your solar collector. That is a part of your system, the part of your house on the construction site. And it belongs to you. Now, if you drill down with a diameter of 15 centimeters, how long can you estimate that it will last, that hole? I say 1,000 years, at a minimum. If you protect the hole from falling down, if you protect it from that, because mud is falling into the hole, then it is just a hole of 50 centimeters and is stable. We know it. So it belongs to the construction site and not to the building. And we see the temperature, that is the temperature curve in Zurich. You have a different temperature curve in Norway. You start not with 12 degrees, you start about with 8 degrees. So that means you have to shift this curve on the other side. That is this side, this increase of temperature with depth is almost equal all over the world if you have this balanced system. What I saw in investigating the system in Norway, this bend here, what this strait goes down to about 150 meters in the Norwegian publication. Interestingly, there are no publication in Norway that goes down to 500 meters. They all stop at 200 meters. So please go down. First in your thinking. So the interesting thing is, in Switzerland, if we have 450 meters down, we are at the temperature of 23 degrees centigrade. That is the same temperature what we like to have in our indoor climate system. Exactly the same. So we have just to connect these things with up and have to accept that we have to have some temperature differences to move the heat from there to there, and that is part of the theory of the system. Now what we did some mistakes. My own house has used a different kind of earth probe like this. That is a new invention now. And I do not tell you about of the mistakes and of the milestones we got until this year. What we do now is, and that is a patent that we wrote about 4 months ago, we drill a hole of 450, 500 meters with a diameter of about 14 centimeters. And normally, if you insert U-tubes, earth probes, you have to fill it between the tubes and the rock. You have to fill it with concrete in order to give a good thermal contact. But now we developed, because of a mistake, said, well, we use a membrane, a flexible membrane. We insert a folded flexible membrane in this hole, and we expand it with water. And this water is used as a circulation system for the whole installation. And we have an overpressure of 2.5 bar we have in every system of earth probe system, because that is the pressure on the expansion system, so expansion tank, there has an overpressure of every system of 2.55 bar. These 2.5 bar, they press this membrane to the wall and protect the wall from damaging and protects the circulation from water in the lower stage and at the stage and so on. And now the interesting thing, if you have protected the borehole like this and filled with water, you can insert a tube that is isolated because you have a bigger diameter, and the question of 500 meter is a question of pressure drop. You have to circulate the water. So we use the big area of circulation, and we insert insulated tube, and we do alternative flow in summer and winter. In winter, we bring, after the heat pipe, we bring a heat pump, we bring the water in the outer space of this coaxial heat pump down, and we reverse it and go and keep the temperature constant because it is an isolated tube. And in summer, we do the inverse. So that is now the curve in summer. And you know, this 30 degrees centigrade corresponds perfectly with this temperature down here of 23 degrees centigrade in the Earth. So what we do, we bring the energy in quality-wise down without any quasi heat exchange in the center, in summer, in the center of our tube, and we cool it out at the bottom, and so we have no negative mixture of quality of energy in the soil. So we heat it up corresponding to the natural gradient of temperature and heat in the soil. We do not disturb the natural system like we do it with every other U-tube system, where we go down first. If we would have hot water, but we bring the hot water up again, and it is cooled out on the upper layer of the soil. So this is the most important invention we did in the last year. That is not new. New is that we do not use this concrete filling of the system using a flexible membrane. And this thing we are investigating, and now at the moment we are transferring it to the industry. I think we will have the first probe down at 250 meters as a first prototype in June, and the first project will be drilled in November of this year. So that is a thing like this, and of course now if we do the inverse thing, we bring, after the heat pump, we want to have a high temperature in the heat pump, so the evaporation temperature of the heat pump should be around 10 degrees centigrade and not lower. So we go down. We have no heat exchange because in Zurich, because the soil is warmer than the water after the heat pump. So we heat it up, and we come up with a temperature of about 17 degrees centigrade. That's the calculation right now. So what we do, we produce waste heat of photovoltaic systems in summer at a temperature of 30 degrees, and we're taking it out in winter at the temperature of about 15 degrees, 17 degrees. We accept degradation. That are the losses. We do not lose energy, but we lose quality. And that is the second law of thermodynamics, because we can add the quality in the winter with the help of the heat pump. So we have to know something about heat pumps. The heat pump has the duty to transfer and transform the heat taken out of this 17 degrees centigrade, that is this one here, to the supply system for heating. Now, if you build new, you can quasi manage a system that runs on 30 degrees. If I have to refurbish Mies van der Rohe building, then I have to accept this 50 degrees centigrade, and I would accept this, so I would have to use more work. The machine must work harder. But this 17 degrees centigrade has nothing to do with the building itself. So now, using thermodynamics formula, do not have the time to explain you that is this interesting formula for calculating the COP, the coefficients of performance of a heat pump. And the COP of a heat pump is this flux here, what we want to have, divided by this, what we have to put in. That is the COP. And the COP of 1 is this heater here. That is the COP of 1. That is a bloody, essentially, a thermodynamically silly heater without the heat pumping, but just destroying quasi high-quality energy. And the higher up you go, the more energy you mix into the system from the soil. And here is a temperature difference the machine has to lift. That is, the pumping up means augmenting the temperature. And that is a temperature lift. If you have a 0 here, you have infinite. That is due to the formula. You divide the temperature by a factor as the temperature difference, and if the temperature difference becomes 0, x, a measure or a figure x divided by 0 is infinite. So you are like here. So what we do now, we try to establish a system with a temperature lift of about 15 to 20 degrees centigrade. That is the thing what we want to have. And that has to do with buildings, that not with a machine. Drilling down to 400 meters means we have one part of this temperature lift we decide on the site, of the construction site and of the regeneration, and the other part has to do with the heating system inside the building. And so the both together is this temperature difference, and we want to do it here like this, bringing up the COP to 12. That's a normal machine with the internal coefficients of performance, that is the friction losses and compression losses and so on of the machine inside. There's a G value or zeta value of 0.5. We are able to produce a machine with 0.6 and bringing up in heating to 10 or 12. And that's what we're producing. So knowing this, that we want to operate the curb-to-turb, the compressor, at a low temperature lift. We go into mechanical engineering, and we know that a piston compressor or a scroll compressor is a bad machine, a bad compressor for low temperature lifts, for low pressure differences. A good compressor for low temperature, for low pressure drops, is a turbo machine. Now, in the market, there exists big turbo machines, 200 kilowatt to 1 megawatt. They are perfect. They run perfectly. They do the COPs of 10 to 12 in the market right now. We have established at the ETH a site with about 300 boreholes at the moment, and running with a turbo machine with 1 megawatt, and is producing the heat, what we need, with a COP of 11. That is right now, it is in operation. So our problem was a small turbo machine. And small turbo machine need a very high speed of the impeller. So that is now the prototype. This picture has been taken 2 years ago. That is the size, and that is a compressor from 10 kilowatt of power, of thermal power. If we go up to 15, what is needed for that corresponds to one earth probe of 450 meters, then it will be a little bit bigger, but let's say 10% more in diameter. This machine is turning with a speed of 148,000 revolutions a minute. That is, again, it was not possible to have motors, electrical motors, with such high speed. That is a thing of the new electrical systems. It was not possible 5 or 10 years ago. This is a spin-off company of the ETH, and they producing motors with 1 million revolutions a minute. And knowing this, I saw this machine and said, well, now we can produce a compressor running on these velocities, 200 revolutions a minute at 20 degrees, and we altern the speed in order to have lower pressure differences. And this is now the measured curves, that is the COP, the G value you see here, that is around 60 degrees. And now my colleague who is doing this in the research in Lucerne, he tells me that they have the new aim of 65% up here. That would be even steepen up here. And that's a fantastic result. It's only possible because of the new technology of high-speed electrical systems. And the other one, we worked together with the best engineer from ABB that produced this turbo compressor for loading up the explosion machines. So that is underway. And if you compare everything together, we can estimate a figure like that. That is a fraction of electricity you need to run a system in correspondence with a temperature lift. So that means in 15 degrees centigrade, you need 10%, 0.1 fraction of electricity. And you can linearize this curve approximately with this formula. That is, it will be much steeper, so much lower in slope, so that you will not have to bring in so much of heat. So that brings us together to a system. That's now, you see, we have, in comparison with the car, we have produced a new clutch, we have produced a new gear, we have produced a new motor, and so on. And now we put it together to a system, and we call it Sol2Ergie. And that comes from the French expression énergie solaire avec stockage au sol. That you see, you have 2 times SOL. SOL, that's why the square. That is a question of branding. So, and now, how does it work? We have the heat pump in the center of this, you know. Then we have this earth probe with 450 meters, one pump, circulation pump. We have the normal system that is operating the floor heating system and also the ventilating devices. And we have a third circuit who brings the energy from the hybrid collector to the thing down. And we restrict from the question of reliability and simplicity that we always go with this heat produced by the hybrid collector down to the circuit into the earth. We do not try to use it in our quasi-circuit in the house. I did it in my own house. We tried to mix it so, and I cut all the material out that is not needed on Monday morning. Last Monday morning, I worked together with the guys, the installators of the firm, and we cut out with the tiger saw about 300 kilograms of iron to simplify it. So what happens actually in summer, we produce this heat that cannot be used, and we transport it with this line, with these 2 circuits into the soil, and we deposit it where it has been taken out 6 months ago. So we replace the heat what we have taken out in winter. That is a question of sustainability. If you take out something out of a system, you have to replace it in the same, in minimum, in the same quality. We do it with a higher quality because we have to accept the quality losses, not the energy losses, but the quality losses in these 6 months. And then in winter, we inverse the flow in this earth probe. We introduce mechanical power via this electrical motor into the system, and we lift the temperature from down to up here in order to prevent or to provoke this energy flow out of the system here. And now it's an interesting thing. That is a storage, as a seasonal storage system. If you have a storage tank and you don't manage them, don't fill it and don't empty it, it's a silly investment. You have to empty it, otherwise it's just a silly investment. How do you empty a store? Through a bad envelope, of course. If you have a very good envelope, you get not rid of the heat down here. And that's a question, now you see it's a question of economics, what is worthwhile, what is more interesting, to invest in these things or to invest in this resistance. That is a question of economics and aesthetics. You can decide. You can decide. You have a parameter more, and that is the choice what you have. And every architect, every single project has to decide what he wants to do. So now again, we have, because of knowing this, we have a new kind of hot water production using that is the heat pump here, as the heat pump section with this circuit of the hybrid solar collector here, the circuit for the earth probe, the heat pump that delivers, that shifts energy into the system of the room. And now we add a new separate heat pump to produce hot water, taking his source heat out of the return quasi circuit of the building. That seems to be silly. But in summer, we use the solar energy coming into the building, hitting the floor, is transported through this machine, and then we can stop all the system here. So we produce the hot water with the heat that comes into the window onto the floor. So we cool the building and produce our hot water. So it depends. In Italy, that is a perfect system. Then you have a cool building, a cool floor, and you have hot water in abundance. In Switzerland, this is quite good because we have augmenting temperatures in our towns. Everybody wants to cool their houses. That's a perfect system. You have to decide. We have to decide in Oslo if it's worthwhile to do this, or it is better to bring it in the same machine and do it alternatively, like it is done normally. But that is a section what you can do it. So the next thing is what we do. We do not use the heat in the exhaust air because we are in concurrence with the heat down here. That is the recovered heat out of this system on the roof in summer. And the heat recovery of the exhaust air is the recovered heat that has been brought in a heat exchanger 2 minutes before the extraction. And this is 6 months before extraction. So we are in concurrence, and if this is cheaper than the extraction of the heat in the heat exchanger in the air system, then we have another choice. So what we see, that it is much cheaper to drill 15 meters deeper per apartment than to install a new system for heat recovery out of the exhaust air. There's a question of system quasi understanding. That's a provocation. And so what we do now, we want to have the air coming into the building either cold in summer or warm in winter. So we have to have a small apparatus with a heat exchanger in it. And you know, if you want to have low temperature distribution systems, you have to have surfaces for heat transfer. What we do, we add heat transfer surfaces into the system by using this ventilator system. And everybody who knows with these fans, you augment the heat transfer coefficients by a factor of 10, having a higher velocity provoked by a ventilator. So these are so small that they can be decentralized, and we decentralize it somewhere in the facade or in the floor system. They have a height of 10 centimeters, though they can go in between the iron layers in a concrete ceiling. And we use the normal exhaust air system out of the kitchen as the position where we extract the used air and the bad air, the polluted air out of our homes. That we need anyway. So what we have done is we lowered the speed of this ventilator so you cannot hear it, and it is just extracting this about 60 to 80 cubic meter an hour that flow in through this heat exchange. That's all, and we push it away without heat recovery. That is a provocation, and it's a provocation as well in Switzerland. So I will show this picture the first time in Switzerland on the 26th of February, and I'm quite sure people will shake their heads. But that's my duty to provoke. Otherwise, I would not be the right person for research at the ETH. So if you look at all the system and you have a flow of energy that is sustainable, what you have seen, we have the solar energy, and you can not only use the waste heat of the solar absorber, of a hybrid collector, you can use the heat of a refrigeration machine in a store or in a hotel or whatever, or the IT center or whatever. Again, philosophically, this heat, the waste heat of a heat refrigerator, is solar energy. That's transferred first. The sun shines on the sea, 100 kilometers, 1,000 kilometers away of Norway. It's evaporating the water. The water climbs up, goes to the height of Norway, is falling down to water. It is transferred into electricity. Electricity is transferred with the grid to the electrical motor of the refrigerator, and is transformed into heat, and then the heat is waste heat out of solar energy. We don't have anything else. So, but this is just an indirect solar energy system. And you can use it as well as you can use the waste heat of a solar panel like I demonstrated you. So we have different possibilities. And if you are able to manufacture the flow inside to have a good comfort, then you can think on the facade, on this resistance of the facade. And again, we know what is comfort. Comfort is when inside temperature of this wall has 17 to 18 degrees centigrade and not lower. That is comfort. And that has to do with our body. Our body feels comfortable if you are in a balanced system of radiation and of inside air temperature. If you have a balanced radiation set of about 18 degrees centigrade, not lower, then you are comfortable in 21 degrees centigrade. If you have a cold surface, you have to augment the temperature of the air. So now, if you know that it's 17 here and outside it's minus 17, have a temperature difference of 34 degrees centigrade, you have a thickness of so on, and then you calculate the necessary resistance or the UU value, and it comes down to about 0.65 and not 0.12. So the necessary U value you have to have for comfort reason and also for the reason of safety of the material is about 0.65. And again, if you want to build new, it's silly to build such a bad envelope. That's silly. Because if you start to do it in new, you come to 0.2 or whatever. That is normal, that's economically reasonable. But in existing building and in nice buildings, you do not have the possibility. You would destroy quasi-cultural heritage and whatever. So you have, normally have 2-3 centimeters at this position. So what we developed in Switzerland as well, we developed the plaster, having a lambda value of 0.03 watt per meter Kelvin, and you can bring it like a normal plaster. You can replace old plasters with new plasters, and then you have this value of what you have. With 3 centimeters of thickness, you add a resistance of 1 to the existing building. And normally you are, with these 3 centimeters of plaster, in the quality of comfort, not of heat transfer. So again, you can decide. Either you have another insulation inside or you make it real big or whatever. So what's the effect? I come to my end. The effect is that can deal with heating systems, with the shifting from a lot of energy from winter into summer, from summer into winter, and staying on the spot, on the location what you are, or neighborhood of about 300 meters. You can resist on these things. But you have to have electricity in winter. And it's silly to think on storing electricity from summer into winter. That's just silly. So then we have to deal with weather, or with climate and weather. What we see in this system of European environment or area, we always have some spots where there is sun, that is a high pressure system, or we have low pressure systems and that are rain or whatever. We know that there is wind from high to low, and we know that we can produce, in this difference here, with windmills, we can produce electricity, and we know that we can, with photovoltaic, produce electricity here. So it's just a question of systems, how we transport and transform where we produce this winter electricity for heating up our buildings with heat pumps. So the question, you're up here, or even north. And what I learned yesterday, that you have maximum power production in your grid of 30 gigawatt. And you have 4 million people. Now in Switzerland we have 10 gigawatt and 7 million people. Something is wrong. So you have to contribute with your electric or with your water power to Europe. We will provide a little bit of height difference with our dams. So, I mean, that is a question of solidarity and a question of exchange things, who is best situated. And that's the thing to do with this meteorology and with this best place, I think, in the world for human beings around the Mediterranean Sea, and you can go up to about 2,500 kilometers up to Oslo. You do not have to go down. Yes, it's okay that you stand about at the border of northern border of Africa, and you use about 50 kilometers of the coast. But this is, I think, the best place for human beings in the world. So the thing is, what are we doing with these towns? That is Bern, the World Heritage of Culture, and these roofs are protected. So we have to deal with the energy consumption with this kind of towns, where we have problems with integrating photovoltaics on these roofs here. So again, this is an interesting development. We know we are working together with a group that have developed a photovoltaic element that has the same color like this terracotta. So we are integrating this terracotta system in different kind of tiles, having similar shape. So we transform again these roofs with another generation of covering methods, because these tiles that are not original. In first years of Bern, they have been straw on these houses, then have been wooden shingles on the houses, and then have handmade terracotta, and that is industrial terracotta. So we continue and said, well, we continue and do it from appearance similar like this, and we use just glass, but it is colored glass. And this first time we will use a roof curvature that produces energy and not only protects the building. That's the first time it is possible to do this. And so it is possible that we replace probably not this one here, but this one here where you don't have them lucans inside. So we look for the interesting areas, and we transform it from these silly tiles into intelligent tiles, and using the energy produced out of these tiles, store it in the energy and so, and sharing with neighborhoods. And there is was this big store, this famous store in Switzerland or in Bern. So they had waste heat in summer and in winter. So we do not release this heat with noisy machines in summer. So we bring the system into silence, not ventilating it back into the environment and the ambient air in summer, but bringing it with silent pumps into the earth and letting flow through the walls in winter outside without any machinery. So what are we doing with this one? That is a Metropole building in Zurich that has been refurbished some years ago, using the limmat which flows by as energy source for the heat pump. That is a good solution, but the river is just one river, and we do not have for every house an own river. So we have to find new sources for the heat pumps, and I think this soil at a depth of about 500 meters is an interesting part. That is my own house. You know that is full of technical development, and you see here these windows here that are special glasses. You will not be able to buy this because that is a prototype, and we developed it further with a company. They are in a spectral reflectance using one layer of silver more in the second position of the glasses. That is 2 silver atoms having a diameter of about 0.1 angstrom, or the nanometer thing, on top of 6 existing layers. So we use a little bit more silver in order to have these glasses inside. They look transparent like normal, but this we do not have to shade. We can avoid this thing here. And that is an experiment what we use now for Singapore. In Singapore there's no external shading, and with these glasses we can save about half of the energy production or the energy need for climatization in Singapore. And it is much better from the transparency than any other system what they have in Singapore. So dealing with this kind of technologies and systems of physics, we are able to overcome the problem what we have. I think, unfortunately, we will not be able to slow down. We can slow down the climate change situation. Unfortunately, I think we cannot stop it. But for our next generations, it's our duty to lower the speed of this change. And if you're interested, you can read on these 2 pages what we work. I want to say at the end that we have an opportunity in the neighborhood of Zurich, that we have excellent firms, small firms, that help us to redo these technologies. And I tell it is not a question of energiewende, it's not a change of energy, it's a change of technology. That is it is a composition of new elements that are known or not known, and that is the possibility that everybody can afford it. The aim is that these systems become cheaper in investment than any other system, and it is possible if we come to a big market, if we have the mass production in high numbers of machinery built on our own, then we are on a price level that beats everything what is on the market now. The question of distributing systems in an international scale. So it's not worthwhile to think on a system like Switzerland or Norway. We have to think internationally to bring down the production costs to a level like cars. That's my last question. Do you know what is the price for 1 kilogram of car? What do you estimate? It is about 6 francs. This heat pump, what we will build, has a weight of about 60 kilograms. You can calculate what it could cost if it is mass-produced in the same manner like cars. We build 100 million cars a year worldwide. If you have 10 million heat pumps produced, the production costs are in the same range. That would be 500 francs for a heat pump. You can forget it. At the moment, you pay about 10,000 Swiss francs for a heat pump. Why? Because every single machine is hand manufactured, and the production volumes of a heat pump is about 3,000 or 5,000 at the maximum. We have to do the same thing like we did in IT systems or whatever. It is computer, it costs nothing in production. So that's the purpose. And so you have to think, we can think on energy distribution and energy flows again. Thank you very much.
Thanks to you as well. This is being streamed and we have to be strict, so we have to ask only one question at a time, and we have to understand the question and we have to repeat the question up here to be able to stream it. So that's the rules. Okay, are there anyone that wants to have some words? Yeah? So the question is, do you need electricity from the grid for this system?
Yes, we need a normal system, like you have a direct heater that discharges electricity directly into heat. You have the COP of 1, and compared with this system's direct electrical heating, we use a sixth or a tenth of electricity disposing on the temperature lift. In addition, we have to have the circulation pumps for the two water systems. That is about 5% of the consumption what the heat pump takes. But that has to be just in time in winter. But it's a fraction of 10% to, let's say, 20% of the system that you use commonly here in Norway with direct heating, or the whole of France is using those direct electrical heating systems.
Do you know that we have a house?
Yes and no.
So the question was,
But not 500 meters.
we also have you have to use the microphones. He said that we also have a house comparable to this one in Norway, but your comment was
Yeah, no, you know, we have in Sweden. At the moment, half of all buildings have new buildings and refurbished buildings have these earth probes, and I think more than half of them to have heat recovery in summer, not to recover, to regenerate the soil, but to cool the buildings. That is the purpose. And they all go to 200 meters, 250 meters. That is the normal boring depth what we have. Because, and again, we had problems with drilling machines. We had problem with the pressures in the U-tubes of damaging tubes and so on. And that is what we know now, that U-tube heat exchange are very bad systems. And the depth of 200 meters with these bad heat exchangers that to bring the heat quality from up, down, and you have a horizontal mixture of heat that are thermodynamically wrong systems. So if you want to go deeper down, you cannot continue with U-tubes because the pressure drop in the tube is too big. Then you would have to drill bigger, and that's so expensive, nobody would do it. So you have to go to coaxial heat things. And if you go coaxial, then you can go deeper. If you go coaxial, then you have the possibility to have inverse flow and isolate it. and isolate in a tube. Then if you do have, then you can switch the things. Then you can use active cooling with turning the machine, the heat pump, with external shift from the flow from cooling, from heating to cooling. And by doing this, you have a possibility to inverse the flow in the probe again as well. And that does not exist, because otherwise we would not have accepted by the patent, international patent system.
So we have systems and solar energy also in Norway, but the point is this system is optimized on all levels. You're thinking systemic.
I don't want to be my own. That's not the way. So the thing is, if you examine, and that's my possibility at the ETH, I can make experiments, and I have made a system evaluation with comparing a heating system with an oscillating electrical system, and that you come to this understanding of dynamic behavior of a system. And that is a question of energy-wise, the quality and quantity. And for me, if we want to lower the energy electrical consumption, that is necessary in Switzerland, not in Norway. You don't have any problem with the electrical grid. We have a problem with electrical grid in Switzerland and Germany and in Italy. So we have to deal with COPs of heat pumps. We cannot accept having COPs of 3. That's impossible. We could not continue into the year 2050 with a COP of 3. So we have to go up to 6, and 6 in the average of the whole stock of buildings in Switzerland means the best things have to be 8 or 10, the new dwellings. And that's why we have to go to 450 meters. That's why you have to use different kind of materials. That's the thing. And we know that all over the world are investigating in the same system, and they don't want to be unique. That is not the question.
There's one question here.
No, that's not my problem. Oh, just I looked.
You said that with making boring holes down to 800 meters in your. Okay. So let me repeat quickly. The first two questions was about the costs of the drilling, actually. You're saying it's probably getting very expensive to drill 500 meters. And the second was the costs of the heating pumps, which you might have some solution on. The third question was about drilling in wet holes, the problems down there. Mm.
So the first question. We know in Switzerland 1 meter of drilling and fixed installation with installation of a borehole system costs about 55 Swiss francs if you have a big site. That are the costs of where these 100 boreholes have made inside of one entrepreneur in a time of about 2 months. That is, then you have to have construction site installation costs, and you can share with this. If you want to drill one hole, you have to displace the drilling machine to place, then you start to drill. That is about 75 to 90 francs a meter. Now, we know that we use about 0.6 meter square meter of length per square meter of construction site, if you have an average size building on top. Now, that means you augment the price of the construction site by about 60 Swiss francs, or the 50 euro. Now I ask you, what is the price of 1 square meter of construction site here in Oslo? It's about $2,000, 2,000 euro. So would you buy it if it cost 2,050 instead of 2,000, but it has a hole in it that lasts 1,000 years and covers you and brings you 90% of your heat? It's a total different approach. It has nothing to do with costs, but has to do with philosophy. So the one thing. The other thing, and that is, I don't mind. I hope that people will earn money in drilling. Otherwise, there's no way of keeping society on life. What should we do with the saved money? Flying to Bangkok or whatever? So the thing is, we have to change our infrastructure, and it has to cost a lot. Otherwise, we do not know what we do with this saved money out of efficiency gain. That's a philosophical question of a society. Otherwise, we game just around, and we bring the money to internet, and we look porno and whatever, and we pay for it. The same kind of money. So we can spend it once. The second is the question of the heat pump production. You know, this turbo compressor that will have a capacity of 15 kilowatt, it will cost about 800 francs, we know, with a construction, with a volume of about 30,000 elements a year. This company, this small company, is able to produce with this system what they have, with the manufacturing capacity, they can produce 3,000 a year, and it will cost 800 Swiss francs. So now you add evaporators, you add condensers and so on, then you come to a price of about 3,000 fabrication cost. Now you have the problem. 3,000 fabrication cost, that will be the price at the end of 2015. You would be able to bring it down to 1,000 in mass production with 1 million. But then it comes to the question, what is the factor from the price out of the factory to the market? In cars, you have a factor of 7. If you build together a car and you just take the prices of the elements in the factory until the price is a difference of the factor of 7. If you have other systems, they are a factor of 4. So the question of how you're distributing it, what kind of people are earning a lot of money in transferring it into society. Again, it's the same thing. The society have to earn. The people have to money has to run. So if it is possible to have a system like 3 as a factor of 3, then it could be in an order of 5,000 Swiss francs and the same price like an oil burner of 15 kilowatt. That is the aim. It has not to be cheaper. And the last question is the question, can we use this energy from the solar energy, or this is 30 degrees centigrade in a wet or a dry borehole? That doesn't matter. The thing is, you have to have a fluid for heat transfer. And the fluid is, of course, it is water. If we know that in winter we have all the time above 10 degrees centigrade. That is the aim. Otherwise, our system is not does not perform. We know that we don't have to add glycol, as some alcohol, to protect it from freezing. That we know. So as soon as you take pure water, you go with pure water in a system where you took the water first out as groundwater to drink. So the same water. And if you have leakage, that is not of interest. Of course, we would not build a system that leaks too much, but a little bit of leakage is actually good. Then we have a control that no dirt is introducing from outside to the membrane to the inner side. So a leakage means we have a distinct flow of water out of the system. That's best what we have. And again, it's other kind of thinking. And we have drilled a coaxial heat tube of 450 meters length that is rolled on a big roll, and it has been transported to the construction site. And this tube has a outer diameter of 9.2 centimeters. And it was so stiff because the producer, Rehau, they thought it has to be pressure proof from inside pressure with a pressure of 46 bar. So they reinforced this tube with an iron layer around it with the weaving, and that makes the stiffness. So the problem was the transport costs have been bigger than the cost for the probe itself, because this diameter is so big and they have to buy a special transport. So when I saw this probe, I said, no way, we cannot continue with pressure-proof tubes, coaxial tubes. That's not possible. So you get rid of the idea of pressuring and withstanding pressure, and you take the ground as a pressure vessel. Then you have a flexible membrane who prevents this backflow from the vessel. That is the thing. So what we use tubes that are used for firefighters. They have 3 millimeters. It's a textile, woven textile inside, and is coated with polyethylene. And we make some little holes in it, so we know that there is a perforation, so that we know we will have at high pressure drops, pressure difference from inside to outside. We have a bit leakage in order to fill up the gaps behind if they are filled with air.
Turn up here, I'll just give you the microphone and you can ask directly.
Have you investigated any possible problems on geological level when using this type of technology with boreholes in a big scale, and any aspects on the ownership to the resources in ground? Who owns it?
Yes, we did it in Switzerland. Because we wanted we are selling this idea to firms, of course, and they did this investigation. What is the risk for drilling 300 or 500 meters? What we know of about 100,000 probes in Switzerland drilled. By the way, we are drilling about 160 firms are drilling with 150 machines are drilling all the time about 2.5 million meters of earth probes a year in Switzerland. And at the moment, there is an average depth of about 250 meters, so we know exactly the risk of this. And the risk of the errors or the not working probes are 0.3%. That is the losses of probes. And that lasts now during about 28 years. So 28 years ago, the first probe has been drilled. No problems with this. So the extension of 500 meters is not very critical. 200 meters of geological part. The belongings, the rules in Switzerland is different like in Germany. In Switzerland there is a law that the the ground belongs to the constructor, to the owner of the land, as deep as you want to go, as long as there's no other common interest against. Common interest against this private use is the freshwater production of the community, or tunnels. Tunnels that is not very often. Out in Switzerland is not very often that you are over a tunnel. And the freshwater, now we are investigating, we're dealing with the authorities of the water authorities, and they said if we use water without any addition, and if we don't use concrete to fill it, then it should be allowed to drill in water protection sites. And that is the most important thing for this distribution of the system. So we are not restricted to any systems. What is problematic, I would not drill if there is a thermal well somewhere with minerals that is used in a neighborhood of 500 meters for a bath or whatever. I would not do it because the risk that you damage the flow is too big. And we have to be careful if we have two layers of water with different pressures. That is the artesische pressure difference. So we have to be very careful that we can handle these different pressures that could have a leakage from one to the other.
One question regarding architecture. I see this is a very interesting system for existing buildings, especially historical buildings. But when it comes to new buildings, how did it influence your what kind of new opportunities did it give you? I mean, can you have larger windows? Can you insulate less? Can you get rid of the ventilation system? How does this affect the architecture?
Yeah. Interesting thing. I have an architecture as a PhD student, and we are looking at roofs. The roof is the most important thing, but because we want to use the roof as a heat extracting system. And then we investigate now the orientation and the angle of the roof. And interesting because we rely on the solar, on the summer sun. We do not have to incline it to this height angle what we want to have. So the thing is, in my house we had of other reasons we had an angle of 6 degrees. That is good enough for self-cleaning it with the rain. And that it depends. So the thing is, I tell the architects, don't make flat roofs. So what we do now is, we know that the costs for this photovoltaic is not in the industry. The costs are almost nothing. They came down to about 100 francs per square meter of solar collector. This is $0.8 a watt peak. That is about 80 francs per square meter. Then you can create a panel. That's almost material cost of glass. The other is just nothing. So if you install a system like this, then you have to connect it with electricity, to connect it with plumbing and so on, and with water. And that is the cost of labor work on the roof. And that's, knowing this, we say we go into prefabrication of big panels, of roof panels. And that's changing the way of building roofs. We still have the carpenter that goes up and does all the sawing and so on the roof itself. And so in prefabricating roofs means we have panels shaped like architects do, normally now with BIM systems, and you shape it perfectly. You have a tolerance of about 1 centimeter, and you put the fixed element with a crane on the construction. You cover the house within 1 day. And now that some carpenters become nervous in Switzerland, and now we're in touch with 2 companies. One company is Powertex, who producing this thick of layer we use for this shape, and the other is a company that is prefabricator in wood. And the idea is, and the aim is that we will prefabricate roofs and set it with a crane, and everything is installed. So we have interconnection of water systems and electrical systems within half a day. And that is also changing architecture, because then you have to, that's not architecture from the point of view of aesthetics, but of how you work. You should...
House. What kind of U values did you use?
Wall thickness is 34 centimeters. We have a special construction. We used Misapor concrete, that is a concrete made out of foamed glass. Also, that's why I have to drink so much wine, because I have to have bottles. And these bottles are foamed up and are quasi cutted in the same way like normal stones have and sand has. And this is quasi glued together with normal cement. And inside the system we have 12 centimeters of expanded polystyrol. That's construction.
House. Almost. Okay, we're on overtime, but I have one question actually, since we're streaming. There was one question on my phone from the Norwegian State Housing Bank. How many square meters can a boring hole of 5 meters serve? How many square meters of living area?
400 meter gives about, but now we have to be careful. In Switzerland, I say we use 0.6 meters per square meter of area. That is about 30 watt per meter of extraction, so that we can have to stabilize the temperature of the borehole. Now, but the extraction energy per meter is different here, because you have a higher temperature degree about 20%. So I would guess that you have to drill about around 0.85 meters per square meter. So that would mean 1,500 square meters.
I have to close. I just remind of the next meeting. No, nå skal jeg snakke norsk. Det nytt, ja. Bare minne om nytt frokostmøte, Brød og miljø, 6. februar. Og da skal det handle om Bream Communities. Velkommen tilbake.